So, good morning, everybody. It's my great pleasure to welcome you to the latest edition of the Pangolin Seminar. Today, Mohammad Ghomi from the Georgia Institute of Technology will speak to us about the shortest closed curve required to inspect a sphere. Over to you, Mohammad.
Thank you very much for the invitation.
So I'll just mute everybody. I'll just mute everybody. So if I happen to mute you, Mohammad, just unmute yourself, okay?
Okay.
So you're muted now.
Oops.
Okay, can you hear me now?
Yes.
Yes.
Okay, yes, I was just about to say that, of course, feel free to ask me a question anytime, interrupt me. This seems to be a relatively small gathering. And thanks also to everybody who can leave their cameras on. So I get a sense that I'm actually talking to people, not just as I said to my cats. Okay, so the title is Shortest Closed Curve to Inspect the Sphere. It concerns with some very basic intuitive problems in Euclidean space. So we have this curve here, gamma, in Rn, and it could be an open curve or a closed curve. And we look at its convex hull. C is the convex hull. Can you see my cursor too, by the way? Maybe not. C is the convex hull.
Not seeing the cursor, no.
Okay. C is the convex hull of gamma. And there are some very basic problems that you can think about. You can put some constraint on the convex hull of gamma. So for instance, you can look at the volume of the convex hull or the perimeter or the surface area of the convex hull, the width of the convex hull. The width of the convex hull is the smallest distance between a pair of parallel planes that squeeze it in every direction. Or you can look at the in radius of the convex hull. In radius of the convex hull is the radius of the largest ball contained in the convex hull. So you fix these things. And you want to maximize the length of gamma subject to these constraints. Or another way to look at it is that you can, for instance, fix the in radius. So you look at all the curves whose convex hull, let's say, contains the unit sphere, and you want to minimize the length. So what is the shortest length curve whose convex hull contains the unit sphere? That's the so-called in radius problem. And this is the problem that I'm going to discuss today, the in radius problem in R3 for closed curve. So I have a closed curve in R3. Its convex hull contains, let's say, the unit sphere, and I want to minimize the length. All these problems are basically open in all dimensions, with the single exception of the result I'm going to discuss today. Of course, in R2, they're quite easy. For closed curve anyways. But even in R2, if you have an open curve and you want to look at the width problem, it's actually quite complicated. The answer looks like a caliper. So even in, but anyways, in R2, they're done. In R3, the only one that's done is the in radius that I'm talking about. The rest of them are open. And then in higher dimensions, they're all open. Okay, so I have then a closed curve in R3. And I assume that it lies outside the unit sphere. So it's not exactly the in radius problem because I assume that my curve doesn't intersect the sphere, but it is very close to the in radius problem. Also, this condition can actually be removed with a bit more work, but I do assume that my curve does not enter the sphere. And the sphere is in the convex hull. So this problem, the in radius problem, was studied by Zalgaler in 1996. And he conjectured that the shortest length should be 4 pi. And the equality holds if gamma is the so-called this baseball seam curve. It's composed of 4 semicircles, each of length pi, arranged in the shape of this baseball seam. So he conjectured that this is the shortest curve possible. And so this is the result that I proved recently with my graduate student, James Wenk. It's available on the archive on my webpage, and it's to appear in Krell's journal. And also, if you're curious to just a little bit more background on the problem, you can go to Math Overflow. This is actually where I saw the problem. It was just completely at random. Just surfing Google 6-7 years ago, I came across the Math Overflow where this question had been posted by O'Rourke. So I became interested, and kind of the solution here is announced with a synopsis of the solution. Before I solved the in-radius problem, the first paper I had written here was on the width problem. If there's time, I also mentioned the width problem at the end. I didn't solve the width problem exactly. I solved the width problem only to within 99.5% of the conjecture. But for the in-radius problem, we have the 100% result that I'll talk about. Anyway, so if you go to Math Overflow, you can get more background. Okay, so this is the proof I'm going to discuss today. So how are we going to prove it? To prove it, first we define this notion of a horizon of a curve. So what is the horizon of my curve? I look at each point on my sphere. I look at the tangent plane at that point, and I count the number of points where my tangent plane intersects the curve. And I integrate this number across my sphere. Okay? So what does horizon measure? Okay, so to see that, to understand the meaning of it, suppose I have, I forgot to mention one thing. So before I continue, so why is this problem called the inspection problem, so-called, and why was Geller interested in it? There is a kind of a physical motivation. The sphere is in the convex hull of the curve if and only if the curve can completely inspect the surface area of the sphere. That is, so what does it mean to inspect? It means that for every point on the sphere, there exists a point of the curve so that the line segment joining your curve to that point of the sphere doesn't go through the sphere. So there is a physical motivation behind it. So you have a planet and you launch a satellite. The satellite wants to survey the entire surface area of the planet. So what is the shortest orbit in which it can travel? Okay, so the convex hull condition is equivalent to the entire surface being visible from the curve. Okay, so I mentioned that because this notion of visibility comes up during our talk. So look at this picture here where I've drawn this cone. If you have a point outside the sphere, then all the points inside that cone, these are the points that are visible to you. The boundary of that is the horizon. So horizons are the set of points where you can just barely see. Okay. Now, so what is this integral that I call the horizon? If you have this point, your point moves along the curve. Now for each point, you have the horizon circle. The horizon circle sweeps some area on the sphere. So the area swept by this horizon circle, as your point moves along the curve, counted with multiplicity, that's the horizon. That's this integral that I have drawn. Now, so it's immediate from the definition that the horizon should be at least 8 pi. Why? Because my curve is closed. So it's going to intersect every tangent plane at least twice. So I get at least twice the area of my sphere. Now we can also define this related notion of efficiency. I look at the horizon of my curve and I divide it by the length, then that's like the inspection efficiency, right? You want to minimize this notion as much as possible. In fact, what we need to show is that the inspection efficiency is less than or equal to 2, right? Because h is bigger than 8 pi. What's the conjecture? The conjecture is that L is less than 4 pi. So it's equivalent to showing that the efficiency must be less than or equal to 2. Okay, and that will be the goal of the talk. Okay, so this inspection efficiency, I have some curve segment, and I look at the area swept by all these inspection circles. I divide that by length. I have to show that this is bounded above by 2. Now note that for any partition of my curve into these smaller segments, gamma I, the inspection efficiency is the sum over I of the horizon of each segment, because the horizon is additive. And so you can rewrite the sum as the length of each segment over the total length times the efficiency of each segment. And these coefficients add up to 1. So the efficiency of any curve is bounded above by the efficiency of each subsegment. So this means that it's enough to find a partition so that the efficiency of each subsegment is bounded above by 2. Now, what makes the problem hard is that there are curve segments with efficiency bigger than or equal to 2. So the partition cannot be arbitrary. You know, you have, imagine that you're at some point in the space, and then you want to move in some direction so that the areas newly seen by the curve, the horizon that you generate, has the biggest area compared to the length that you travel. And so given your distance from the sphere, you want to figure out which direction to move so that you maximize this efficiency. Well, the direction that you move, actually, it turns out it depends on your distance from the sphere. So the problem that we're trying to solve doesn't have a local characterization. You cannot completely localize it. If you just want to, if you're at some point in space and then you want to travel a short distance to maximize the area surveyed by the curve, you have to move at some angle. In the final solution, of course, that angle is always 90 degrees, right? This baseball curve, it turns out to have a constant distance square root of 2 from the sphere. So the optimal solution is achieved when you maintain this constant height. And this is not something that, as I said, locally evident. So you cannot localize the problem. That's what makes it difficult. One of the things that make it difficult. Okay, so I've divided it into a number of steps. Step 1, we can assume that a minimizer exists. So I have this curve, the unit sphere is in its convex hull, and I know there must be a curve which minimizes length among all these curves, and it's not difficult. It's just basically the Arzela-Ascoli theorem. Arzela-Ascoli theorem quickly gives you the existence of a minimizer. Now, once the minimizer exists, then one can compute this estimate for this angle alpha. This angle alpha turns out to be very important. The angle alpha is the angle between position vector of your curve and its velocity vector. it turns out that this angle is always bigger than inverse sine of the inverse of distance. And this is a simple calculation. So look at gamma and look at this cone that I have drawn. If this curve wants to minimize its length, then there is no reason that it should enter this cone.
Can
Right?
I ask a question,
Yes,
Mohammed?
yes.
A priori, your length minimizer is only Lipschitz, isn't it? So you don't.
Yes,
You
yes,
don't
that's
have this
right.
angle.
It's Lipschitz, but that means it's differentiable almost everywhere. So alpha exists almost everywhere.
Okay.
So this estimate is almost everywhere.
Okay.
Yes. Yes, excellent question. But because this is a basic problem in integral geometry, we integrate all the time. Differentiable almost everywhere is all that we need. Yes. So so you want to minimize the length, right? And this is the curve, minimize the length subject to the constraint that your curve views the entire planet as efficiently as possible. So if you have a point of the curve and then you have this vision cone, there is no reason for the curve to enter that vision cone because it already sees everything at the vertex of the cone. So the curve, which has minimal length, is disjoint from the vision cone. And that gives you this estimate just by elementary trigonometry. Okay, next, we can compute the efficiency. So to compute the efficiency, remember, efficiency, so its length, that's this 1 over b minus a, and then rest of it is the horizon. So again, remember what's the horizon? Horizon is these circles that are swept on the sphere. Now, this function that I have written here, ft theta, it parameterizes each horizon circle. So t is the variable along the curve, theta is the parameter which goes around the circle. So I have this function which parameterizes my circles, and f inverse of p, as I have written here. Okay, so since I don't have a pointer, maybe here, let me use my pen. So you see this f inverse of p is the same as gamma inverse of TPS2. And this is the quantity that we integrate in order to define the horizon. So this is just then the area formula. The horizon is this number, the number of inverse images that I have to integrate. So by the area formula is just the integral of the Jacobian. So you just have to compute the Jacobian of this function that I have here. And that gives you this formula. So now if you look at the formula, I guess the thing that we can note is that the efficiency depends only on the distance from the center, on the norm of the curve, plus the angle that the curve makes at each point with the position vector. Okay. Now, so here's a geometric part of the proof. This it's a very nice operation. I call it unfolding. It was used earlier in a paper on knot theory, on knot energies by or knot thickness by Kostner, Sullivan, and Cantarella. This is a very nice operation for curves. If you have a curve in space and then connect from the origin all these rays to it, you generate a ruled surface. It has intrinsic gas curvature 0. So it can be isometrically developed into the plane. You take this conical surface and you unroll it into the plane. Then what it does to the curve is called an unfolding of the curve. Why unfolding? Because this operation preserves the length of the curve. You're doing an isometric embedding of the surface. And yet what it does is that it increases all the extrinsic distances between pairs of points of the curve. So let's call this an unfolding. Now, look, this operation does not change the distance from the center of the sphere. So the norm of gamma is preserved. And another thing is that alpha, those angles alpha are also preserved. So it means that when you unfold your curve, it has the same exact efficiency, because remember, the efficiency depends only on the distance from the center and the angle. So this is nice because now you have reduced your problem from a problem in space to a problem in the plane. Although notice that when you unfold, then it's not necessarily going to be a closed curve anymore. It will be just a curve that spirals around the circle. Okay, so remember the goal was to show that the efficiency is less than or equal to 2, but that efficiency is the same as the efficiency of the unfolding. So I just need to show that the efficiency of the unfolding is less than or equal to 2. And then remember, to do that, it's enough to partition my curve so that the efficiency of each partition is less than or equal to 2. Okay. So we have the unfolding. Now, another geometric observation here that comes in really handy is that if my curve is length minimizing, then when I unfold it, the unfolding is going to be locally convex with respect to the origin. So the unfolding is not going to be a convex curve because it just spirals around the origin. You know, you don't know how many times it goes. So globally, it will not be convex, but locally it will be convex. So locally convex means that at each point, I have a tangent line so that the curve lies locally on the same side of the tangent line where the origin lies. So the curve always curves towards the origin. So why is that? Well, suppose it's not convex. Yes?
I have a question.
Yes.
It's regarding step 3.
Yes.
So you said that the unfolding curve doesn't close up.
No.
So what's the constraint here? I mean, what can you say about the unfolding curve? If it doesn't close up, I mean, obviously it's not a point. It's not reduced to a point. It has to be something.
Yes. So the constraint actually is mentioned in step 4. The constraint is its local convexity.
And that's it?
The constraint is its local convexity, and that's it exactly. I'm going to reduce the whole problem just to a planar problem.
All right.
So,
I mean, but don't you want something a little bit more global? I mean, because I don't know. It seems that
no, there will be something more global. Yes. So there is a little bit of a subtlety. I think maybe it will become a little bit clear in step 4 and 5.
Okay. All right.
So the structure of this curve is actually subtle. It has to be locally convex, but then there is even something more subtle that I'm going to discuss.
Okay. All right.
So
thank you.
Yes, thank you. So why is it locally convex? Well, you see, if it's not locally convex, then I can shorten the length of the unfolding, right? But if the unfolding is shortened, then the actual curve will also be shortened. Once I take my cone and fold it back up, right? I had this curve in space and I made this cone, I unfolded it. Now, if I replace this segment here by a straight line segment, then I take my cone, I fold it back up in space. So now I have created this shorter curve. The shorter curve lies above the original curve. Because it lies above it, it still sees the whole sphere. You see? So this operation that I do is going to shorten the length without costing you any inspection. It still surveys everything. So this curve, I need to decompose it into a bunch of segments so that the efficiency of each segment is less than 2. So it turns out that it satisfies this decomposition that we call a spiral decomposition. So what's a spiral? So I guess this is the part which is subtle. Spiral is a locally convex curve with respect to the origin, like I have drawn here, so that the distance from the origin is non-decreasing. It always gets bigger, so that at its starting point, it has to be orthogonal to its position vector. So orthogonality is very important. It starts orthogonal, it's convex, and yet its distance is always increasing. It turns out that this unfolding can always be decomposed into these spiral bits. And once we do that, then the whole, it all comes down to showing each of these spirals has efficiency less than or equal to 2. So now this is like the most local version of the problem. It's a problem just in the plane. You have this curve, which curves towards the origin, which is orthogonal to its initial position, and its distance from the origin is non-decreasing.
Sorry, Mohammad, could you
Yes.
explain condition 4 again? What does it mean, gamma of alpha? In the definition of spiral curve.
Oh, sorry, gamma of, yeah, this is alpha, but actually this should be A. This is the initial point.
Okay, thanks.
Yes, this is A, and this is, yeah, this is this is alpha. That's right. So this is alpha of A. So alpha was the angle between the position vector and the tangent vector. So this is the initial angle. The initial angle has to be orthogonal.
Yeah, and
Yes.
gamma of A greater than 1 just means that the distance of gamma of A from the origin is more than 1.
Yes, thank you.
Thanks. Thank you.
Thank you. Okay. So anyways, so we now have a purely planar problem. Okay, now you think it's easy, but it's not so easy because the efficiency is given by this integral up here, remember? And this integral is still pretty complicated, even though the curve is simple. Okay, so how to get the handle on this integral? Oops, sorry. I don't know what happened. Okay, yes. Okay, so step 6. Okay, so I want to compute the efficiency of these spirals. Now it's enough to just consider polygonal curves, okay? If you do it for polygons, then you approximate and everything works. So let's just look at the efficiency of a straight line segment. So if you have a, if you have a straight line segment, its horizon is this shaded area that I have drawn. The horizon are these vision circles swept by your line segment. Now, one interesting thing that happens is that, and it took me a long time to figure this out. The area swept out is contained in between 2 circles. So all these vision circles, they're fixed. There are 2 points on the sphere that are visible by the line as you move along. So the horizon is just the sum of the area of these 2 looms. So here, H0 and H1 are the distances of these points, P0 and P1 from the origin. And if you have these distances, then you can compute this shaded area. So this formula that I've written, H0 and H1, gives the area of this shaded region. This is the horizon of a line segment. Now, so this horizon, you can divide it by the length. The length here is square root of H1 minus H0 squared. And so this graph that I have here, this is efficiency of a line segment, where the initial point is orthogonal to the position vector, right? So that's the most simple spiral curve. And when I draw the efficiency, you see that if you can see, there's this number 2 in the corner of the box. So for these most simple of spirals, these line segments, the efficiency is indeed always less than or equal to 2. Okay, so for one line segment, you're done.
Sorry, Mohammed.
Yes, yes.
Maybe I'm a little bit lost.
Yes,
What are H0 and H1?
These are the heights of the points P0 and P1. So these are the initial and final heights of your line segment.
Thank you.
Yes.
But in your picture,
yes.
the initial direction is not orthogonal to position, is it?
No. This picture is general.
Ah, right. Okay.
Yes, this picture is general. The formula is general. However, when I do this graph here for efficiency, I did assume orthogonality. Yes.
Okay.
Okay. Very good. So we solved the most simple case, the case where my spiral is just one line segment. So now look at the spirals with multiple line segments, let's say with M line segments. And in the class of spiral with M line segments, then again, there exists one which minimizes length. And so you take, or minimizes efficiency, I should say. There exists one which minimizes efficiency. And we're going to do a variation. I'm going to take the first segment of that polygon and then variate that first segment just like this. So I'm going to vary that first segment so that it still remains a spiral. It means that it has to be orthogonal to its position vector. So it has to move along a circular arc whose center lies on this line from O to P1, the second vertex. So now I'm going to compute the total length for this variation. Of course, the amount the length varies because all the other segments are fixed. It's only your first segment that changes. So what matters is the rate of change in the length of first segment, horizon of first segment, and then efficiency is determined by the change in the length of the first segment and the horizon of the first segment. So if your polygonal curve had, was a critical point of the efficiency, then E prime 0, so I have this variable t. At time 0, E prime of 0 is 0. Now, efficiency, remember, was the horizon divided by length. So this here is just the, I'm just differentiating, and this is equal to 0. So I obtain this relationship. H prime of 0 divided by L prime of 0 is exactly the same as H0 divided by L0, which is efficiency of P. So the efficiency of my polygonal curve is just the rate of change at 0 of horizon divided by the length of change of L at the horizon. Now, the length of change of L, it's very easy. I can just compute that. It turns out to be R over this quantity where R is the initial height. So R is the norm of P0. H prime of 0, I can also compute. The computation will be longer because I had this, remember I had this formula that I had shown you here. This formula is more complicated, but nevertheless, when you compute it, it simplifies very satisfactorily. Now you take the ratio and then you obtain this nice function, 4 times square root of R squared minus 1 over R squared, where R, remember, is the initial position. And this function is always bounded above by 2. And it's equal to 2 precisely when R is the square root of 2. So this solves the problem for polygonal curves. Okay, somehow.
Yeah,
Yes.
just another the questions, just to make sure I understand. So
Yes,
when you
yes.
decompose your curve into polygonal curves, so each segment is segment.
Sorry, no, sorry. I decompose them into spirals. So now I just need to study the efficiency of each spiral. In order to study efficiency of spiral, I replace each spiral by just polygonal spirals. So now I have polygonal spirals, and the goal is to show that the efficiency of each polygonal spiral is bounded above by 2. So yes.
But is it clear that you can approximate a spiral by a polygonal spiral? I mean, like, because you want each segment to be orthogonal to your.
Yes,
to the
so the initial, that's right. So the initial segment has to be orthogonal, which means that the initial point of the polygonal segment is not on the curve, but just a little bit below the curve.
Oh,
Yes.
okay.
So you just move that a little bit down. Yes.
Yes, but
Yes.
okay, all right, and the approximation is not necessarily continuous, is it? I mean, do the segments?
You have a spiral. All you need,
right.
all you know about it is that it's rectifiable. And so it turns out that any rectifiable spiral is rectifiable because it's locally convex. And any rectifiable spiral, you can approximate by this polygonal curves. You have to be a little bit careful, as you said, because you have to maintain the condition of orthogonality. But that's done by just perturbing your first segment just a little bit. And then maybe you have to be careful how you choose the subsequent segments.
Yeah. Okay.
Yes.
All right.
You have to be a little bit careful, but it can be done.
Okay.
So
Thanks.
then so the problem just becomes polygonal. Once it's polygonal, then you do it for just one segment, and then using this variation of the one segment, then you can prove it for any polygonal spiral. Okay, so the polygonal spiral satisfied the bound that you wanted. So you take the limit, and then we obtain the this upper bound for the spiral of for the efficiency of all spirals. So this proves the inequality. Proving the inequality. Yes, sorry.
Just ask, so
yes.
basically what you have is you've introduced a number of simplifying steps, and in each simplifying step, you know that you increase or decrease efficiency. So that when you get to quality, then that means that in each of these simplifying steps, you get to quality. Is that how it works?
Yes, so proof of the equality, well, proof of the equality was hard, let me say that. No, it doesn't quite work like that, because you never have equality for these polygonal curves. You see, the baseball curve that I had shown, it has constant distance square root of 2 from the origin. So when you unfold it, you just get a segment of a circle of radius radical 2. So that's why analyzing equality is still hard, because for the polygons, you never have equality. So in fact, proving the inequality is less than half of the paper. Most of the paper is devoted to proving the equality. So, and I'm not going to go through that too much. I'm just going to give you kind of a flavor of how the equality takes place. So to do this, you can define this notion. Let's call it instantaneous efficiency. So instantaneous efficiency is when you take the derivative of the horizon. So you have this curve, and you're moving along the curve, these vision circles sweeping some area. So it's just the rate of change of horizon that we can call the instantaneous efficiency. Now, if you compute if you make a computation, it turns out that the instantaneous efficiency is this function. Again, it depends only on the norm and the angle. And this function you can compute. By the way, there is a mathematical notebook also on my website that, you know, a wonderful thing about Mathematica is that now it does symbolic computations. So, you know, in this paper, the proof involves no numerical estimates. There is no numerical math that we had to do. Everything was done precisely symbolically. However, Mathematica is pretty good at symbolic computations. If we had to compute these things by hand, as we did, sometimes I think some of these computations would be almost hopeless. Okay, so this is the formula that we have for instantaneous efficiency. So it depends only on the height of the curve plus this angle. Now, this region omega, so this is the pair of all possible heights and angles for a distance, for a length minimizing curve that inspects the sphere. And remember, we had this constraint always for the angle alpha that I showed, that angle had some constraints because it cannot enter that vision cone. So this is a picture. On the right, you have the phase space. This is the set of all pairs H and A that are a priori possible. This is the set of all heights and angles that your curve can have. And then we have the efficiency. And then, so a very annoying thing that happens is that if you look on the right, you see the instantaneous efficiency goes above 2. So there are certain heights so that if you have the right angle, the efficiency goes above 2. This, what I was saying also in the beginning of the talk. The problem doesn't have a local solution. Now, if the initial height is bigger than square root of 2, it turns out that you never enter this region. So the bad region here is bounded by this red curve that I have drawn. If your initial height is bigger than square root radical 2, then it avoids that bad region. So then the instantaneous efficiency is always less than or equal to 2, and things work well. But if the initial height is less than 2, it will enter that bad region. So more work is needed. Okay, so and you know, I haven't included the details because the details get technical, but basically the main idea was just this, right? For the polygonal curves, I just did this variation of the first segment. Now, I mean, it's a little bit difficult for me to summarize. I'm trying to tell you something meaningful, but also concise. But we basically generalize this variation that if I have a line segment, then so you can do this step, but then you move the first segment a little bit up, then you choose another point on the curve, and then you move it a little bit up again, and you kind of do it in a sequence of steps, and then you increase the number of steps, and then you write some integrals which control how much the efficiency changes when you do this variation. Anyways, maybe there was a better way to do the equality that we did, but half of the paper was devoted to analyzing equality because this local situation, as I said, it's not good. Okay, so you achieve equality, and so when you have equality, efficiency is 2. Now, by the stuff I said before, when the efficiency is 2, you know that your curve already has constant height. So your curve lies on this, you know, it has constant height radical 2 because of this formula that I showed here. You know, this formula is equal to 2. Let me show you which one. This one. Here, this is equal to 2 only when the height is constant radical 2. So when the efficiency is 2, my curve lies on a sphere of constant radius radical 2. So now we want to show that this curve that lies on this sphere of constant radius radical 2 is composed of 4 semicircles, right? That was the conjecture. It's composed of 4 semicircles. And for that it turns out follows from a generalization of the Crofton formula. So remember that, it's like the first time I saw it was in Milner's proof of the total curvature of knots. If you have a curve on the sphere and you look at all the great circles, and then so you integrate over all the great circles, the number of times that the great circles intersect your curve, it gives you an estimate for the length. Now that formula can be generalized. Instead of looking at great circles, you can look at the circles of some fixed radius, smaller than the radius of the great circle, okay? This curve that you have is at constant radius, constant distance radical 2. So all the vision circles are these circles traveling on your sphere, but they're not great circles anymore, okay? And each of these curves intersect your sphere. Each of these vision circles intersect the projection of your curve on the unit sphere. In fact, it can be shown that each of these curves intersect these spheres exactly twice. And these have a certain radius. The radius is pi over radical 2. And so it turns out that this is a characterization for the spherical curve. Okay, so sorry, it got a little bit confusing. Let me just express the whole thing kind of cogently. The baseball curve on the baseball curve, which lies on a circle of, on a sphere of square root of 2, right? It's a baseball curve only if and only if its projection into the unit sphere is a baseball curve, right? If its projection is composed of 4 semicircles, then you're done. Now the projection has the property that it intersects every circle of some fixed radius. That radius is actually pi over radical 2 in exactly 2 points. And that characterizes the baseball curve. So the baseball curve is the only curve on the sphere which contains the origin in its convex hull, and it intersects every circle of this radius exactly twice. And this picture that I have drawn.
Can I just ask, I'm a tiny
Yes.
little bit confused. So is that the content of this theorem that you've stated here, or is that your own result? So is that the content of Crofton-Blaschke-Santalo's theorem, or is that your own result about the?
So here we have the Crofton-Blaschke-Santalo, but Crofton-Blaschke-Santalo implies the second lemma. It forces the intersection of each of these circles to be exactly 2, because I know what the length is now. The length is 4 pi, and I project it into the unit sphere. So then the length becomes 4 pi divided by radical 2. Right. But that length is related to the number of times that these circles intersect my curve. So Blaschke-Santalo, together with the length, which I know exactly what it is, give me the second lemma.
Okay.
And the second lemma characterizes the baseball curve.
I see. I see.
Yes.
So
Yes.
the characterization of the baseball curve, that's also something you guys proved. That wasn't.
That's right. Now that takes also like 4 or 5 pages, but
Right.
but now you know what you have to do.
Okay.
And it's doable. Yes, it's just all kind of synthetic arguments. There's really no analysis there. It's just kind of a neat geometric characterization of the baseball curve. The fact that it intersects all the circles of this radius exactly twice. Almost all of them, right? You don't have to worry about all the circles, but almost every such circle intersects it exactly twice. Okay. So I wasn't sure how much time was available, so I just threw in a bonus. I guess I can allow time for questions. You asked some questions too. Anyways, maybe I'll quickly do the bonus, the width problem. So I told you in the beginning, the width problem I didn't completely solve. The in radius problem is solved. The width problem I solved only up to, for some crazy reason, 99.5% of the conjecture value. So what's the width problem? The width problem is the same. You have this convex hull, and the convex hull has a certain width. So the width, remember, is the shortest distance between a pair of parallel planes. And so what I proved is that L over W is bigger than square root of 16 plus pi squared. And this is 99.443% sharp, because this example that I've drawn here, this is a curve that you can draw on the cylinder. It's composed of 4 helical segments. If you compute L over W, it comes within 99.5% almost of this value. So unlike the in radius problem, there is even no conjectured curve for the optimal curve for the width problem. Okay, so it turns out that this curve that I've drawn here, it's not optimal. It can be improved a little bit. So how do you prove this? The proof of this is short. This is the first paper I had on this subject, which is announced on Math Overflow. So by Borsig-Ulam, it turns out that whenever you have a closed curve in space, you can position it between a pair of parallel planes so that the curve intersects each plane exactly twice, and it goes up and down in alternating fashion. It has a nice proof which follows from this topological result of Borsig-Ulam. Remember, Borsig-Ulam says that any mapping from S2 to R2 must have a pair of antipodal points that go to the same value. That somehow implies this. So once you have this, then you can take your curve, you can project it down to one of these planes, or you can project it to the orthogonal line. So if I project it to this orthogonal line, then the length of that projection will be, oh, I see there's a typo here. The length of that projection will be bigger than 4W, right? Because it goes up and down twice. Now, if I project it down, it still has the width W. So by a theorem of Cauchy, its length is bigger than pi over W, because you can compute the length by projecting into all these directions. Now, the length projection satisfies this kind of a semi-Pythagorean property. The length is bigger than square root of some of these lengths, but these we have estimates for. So you quickly get this estimate for the width problem. So the width problem is solved. The in radius problem is solved. The width problem is open. Both the width and in radius problem are open for non-closed curves in space. And then everything is also open in higher dimensions. Okay, thank you very much.
So everybody, please unmute your speakers so that we can thank Mohammad for a lovely talk.
Thank you.
So, any questions? Just wait 10 or 15 seconds. There's always a small reaction time in Zoom.
So Mohammad, can you explain why this curve in the cylinder is not optimal?
Yeah, this curve on the cylinder is not optimal because I can find a better curve. What is that better curve? The better curve, so I can show you if, let's see, if we go to my, I can show you what the better curve is. So if you go to my papers here, so what I talked about is this paper 41, shortest closed curve to inspect the sphere. Before that, I had this paper here, length, width, and in radius of space curves. And here, Zalgaler's L5 curve. So it turns out that Zalgaler actually had a conjecture for the width problem. Zalgaler had actually had a conjecture for the width problem. So this width problem, his conjectured curve was, let's see if I have oh yeah. This is his conjectured curve, the conjecture that Zalgaler had. So it's a curve that goes up and down twice. Each of these segments is a tangent to a sine of to a side of this tetrahedron, and these curves were composed of segments. So each of these segments, it has two straight lines in the beginning and end, and in the middle has a helical side which goes on a cylinder. So he had conjectured these curves to be the optimal for the width problem. And so these curves give you a better answer than the cylindrical curve that I had shown. But these curves are not optimal. So actually, this conjecture of Zalgaler was false. So this curve doesn't give you the best estimate as I demonstrated here. So sorry. So let me actually recall. So why was his conjecture false? I think his conjecture was false because he had made a mistake when he had computed the length. Yes. And I noticed that mistake. So yes. So this is better than the cylinder, however, not good enough.
Okay, but do you still have a candidate that beats this one?
No, I don't have a candidate.
This one is not optimal, it's a sort of deformation, but you don't know what is.
No, I don't have a candidate. Has been a while since I thought about it. No, but the situation is strange.
No, I'm confused. You know it's not optimal, but you don't have an example which is better. How do you know it's not optimal?
Sorry?
I'm confused here. How do you know it's not optimal?
Which one? The cylindrical curve or the
better one of the two? The better one of the two, which as I understand is the one in this figure. How do you know it's not optimal?
Yes, that's right. The best one of the two. Now, actually, yes. And actually, I'm also kind of misremembered. Actually, I forget now whether the best one is the cylindrical one or that one. How do I know it's not optimal? I guess maybe it's a good question. That's right. The best one of these two. That's right. I guess the best one of these two is the best one I know. And how do I know it's not optimal? I guess I don't know. I guess I don't know. But
So
but anyways, but there is a difference.
You believe it's
there-
not optimal, but you don't have proof either way.
No, all I know is that there is a gap. There's a very small gap between the best bound I can establish and between the numbers that these examples that give me.
Okay.
But actually, at the moment, actually, I forget which of these were more optimal. I know that the Zalgarer was wrong. So I think maybe the cylindrical curve actually turned out to be more optimal. I don't immediately remember.
So either your estimate is not effective, or the curves are not optimal. It's one or the other.
Yes, which is very crazy because the estimate that I had, the proof is beautiful. It uses Borsig-Ulam, right? If the proof is beautiful, it should be right, no?
Well, that's good motivation for conjecture. For me, that's a good enough answer, actually.
Yes.
Can I ask? Maybe it's just me, but I didn't see where in your proof you were specifically limited to the three-dimensional case.
Where in the proof was I limited to the three-dimensional case? Yes. So the unfolding you can do in every dimension. Yes.
Is
the
it in the
unfolding-
characterization of the tennis ball curve?
The characterization certainly would require the dimension, certainly. Yes.
Right.
Do we even have a conjectured answer?
Sorry, the characterization certainly requires the dimension to be 3. Now this estimate efficiency is less than or equal to 2. I think that holds in all dimensions, but actually in higher dimensions you can do much better than that. Yes.
Do we even have conjectured answer in dimension 4, for instance? Like the equivalent of baseball curve. Do you have a curve with conjecture with this best curve?
No. With my students and with using Mathematica, we went on some kind of a feverish period, lasted like 2-3 weeks, that every day we were drawing these, a lot of curves that you can draw using sine and cosine, and then you have 4 functions, right? So you take 4 functions and then you write all kinds of combinations with sine and cosine, and then you do all kinds of crazy things, but we didn't come up with a conjecture.
Would it make sense to ask what happens asymptotically as the dimension tends to infinity?
Yes. No, that makes sense. There are some estimates that you can do. Some crude estimates are not difficult to do. In fact, after this paper, a paper came, it's in the field of computer science. Apparently this has some application to computer science, where you have like these planes that pass through the origin, and then you want to have a curve that basically intersects all these planes. Now, it turns out that was equivalent to this inspection problem, and that problem you can ask in every dimension. So there is this estimate, it's a bit of a rough estimate that you can do, and then you can look at the asymptotics of that. But that estimate was far from ideal. I don't know what is the optimal asymptotic estimate. But apparently it had some application in computer science. This paper was in the field of computer science.
I have a feeling as well that these ideas must have some application to Teichmüller theory. I'm guessing that's probably what piqued Andrea's interest, especially in this topic. I mean, if you take a curve in the ideal boundary of a hyperbolic space, and you look at its convex hull, then one of the variables that's of interest. Cats arrived. one of the One of the variables of interest is the width of the convex hull. And Andrea can correct me here, but I think it's interesting to know, for example, what would be the minimal constant of quasi, what's the word, Andrea? Quasi, when you have a quasi curve, it's what's
Yeah, but the length does not make sense in this context. So
no, the length doesn't make sense, but you have the quasi, crikey, I forget the word, quasi-conformality. It's not quasi-conformality, it's quasi-symmetry. The quasi-symmetry constant of the curve for a given fixed width in your convex hull. That would make sense. That would make that would be a question to ask, wouldn't it, Andrea? You could actually ask the same thing for the fixed volume of the convex hull as well, if you're looking at the co-compact case. Does that make sense?
Yeah, it does make sense to me. I'm just thinking. I think the point is that it's probably not true that the curve is a quasi-symmetric, let's say, if and only if the width is finite. So that's some sort of okay, we can discuss this maybe privately, but
right,
I don't.
right.
Yeah, it might be tricky, but yeah, it perfectly makes sense to ask this kind of question.
And you can do the same thing. I mean, that's hyperbolic. You can. It's very natural to do the same thing in anti de Sitter and so on. Let me think for a minute. Are there any other questions?
Oh, by the way, let me say that, okay, I remembered by reading my own paper here, as it says that, so the cylindrical curve is better than this curve that Zalgaler had conjectured.
Right. That would make sense,
So,
actually.
Yes, his construction was very complicated. There was a subtle mistake that he had made. It took me a long time. The paper actually was also in Russian to make things more difficult. But so the cylindrical curve is the best estimate now. I think there was a reason. I don't know why you see, here's the conundrum. The conundrum is that the proof using the Borsig-Ulam theorem is very natural, but then the cylindrical curve is also very natural. And yet there is a gap in between of 0.5%. Okay,
Right.
so that's the status of the width problem.
I guess we should call it a day there, because it's already 11:45. So let's thank Mohammad once again for really nice talk. Thank you, Mohammad.
Okay, thank you.
Really nice result as well. So before I stop recording, I just want to do a little bit of advertising for the next edition of the Pangolin Seminar. So let me just set things up here. Share screen. So, as you know, the next edition of the Pangolin Seminar will take place in exactly 2 weeks' time. That will be Tuesday, the 9th of November, same time, Rio de Janeiro time. We don't have summertime here, so the clock's time in Rio de Janeiro is not going to change. And our speaker will be Nicolau Saldanha, who is here present today from the Catholic University of Rio de Janeiro. And he is going to talk to us about the homotopy type of spaces of locally convex curves in the sphere. So hope to see everybody there in 2 weeks' time. So once again, thank you everybody for being present. Thank you, Mohammad, for a lovely talk.
Thank you.
I'm going to stop the recording now.